the neutrino experiment is very difficult, and only a few experiments running in the world.
In Japan, scientists are hollowing out an entire mountain for a purpose that's left the world stunned. But why go to such extremes? What secrets could they be hiding in the darkness? From advanced neutrino sensors to earthquake-proofing marvels, this project isn't just about science, it's a peek into the future of discovery.
Then this discovery of neutrino oscillation provides some window.
Join us as we explore the shocking story behind why Japan is hollowing out a mountain. The mountain project that has captivated the world. Engineers and scientists are quietly hollowing out an entire mountain, creating a massive underground chamber that will house one of humanity's most ambitious scientific endeavors, the Hyper-Kamiokande Neutrino Observatory. Picture this, a colossal dome-shaped cavern, standing over 309 feet high and 227 feet wide, buried 1,969 feet beneath a mountain peak. This extraordinary feat of engineering isn't just another construction project, it's a $600 million investment in unlocking the universe's deepest mysteries. Here are some mind-boggling facts about this project. The Hyper-Kamiokande is a dome-shaped water tank that will hold 260 million liters of ultra-pure water, equivalent to 104 Olympic swimming pools. We will go into details much later. This project will house about 40,000 ultra-sensitive photodetectors lining the chamber walls. Also, 21 countries are collaborating in this groundbreaking initiative, with the construction timeline spanning from 2021 to 2026. But why would Japan invest such astronomical resources into hollowing out a mountain? The answer lies in the hunt for one of nature's most enigmatic particles, the neutrino. But there's more. These ghostly subatomic particles zip through everything in their path, including our bodies, carrying potential secrets about the universe's creation and evolution. They provide insights into fundamental physics. They help us understand stellar processes. They offer clues about cosmic phenomena, and they contribute to our knowledge of particle interactions. The Hyper-Kamiokande project represents a quantum leap in our quest to understand these elusive particles. Hidden beneath tons of rock, this sophisticated detector will capture the faintest whispers of neutrino interactions, potentially revolutionizing our understanding of physics and the cosmos. This is beyond a Japanese achievement. It's a depiction of human ingenuity and international collaboration. Scientists, engineers, and constructors from across the globe have united in this bold venture, pushing the boundaries of what's possible in scientific exploration. The implications stretch far beyond pure science. The technologies developed for this project could spark innovations in medical imaging, environmental monitoring, and engineering. Each breakthrough in neutrino research brings us closer to unraveling the fundamental mysteries of our universe. As construction crews work tirelessly beneath the mountain, they're not just building an observatory, but crafting a gateway to understanding our cosmic origins. When observations begin in 2027, this hidden marvel could unlock secrets that have puzzled scientists for generations. Now that we know the purpose of the project, let's explore the particle at the heart of it all. The fascination with neutrinos, understanding the basics. Right now, trillions of ghost-like particles are passing through your body. These mysterious subatomic travelers, known as neutrinos, zip through Earth at nearly the speed of light, completely invisible to our senses, yet fundamental to the fabric of our universe. Neutrinos, unlike protons and neutrons, are incredibly light, nearly massless particles with no electric charge, making them extremely elusive. While protons and neutrons, found in atomic nuclei, interact strongly with other particles due to the strong nuclear force, neutrinos interact only through the weak nuclear force and gravity. This weak interaction allows neutrinos to pass through almost any matter undetected. While protons and neutrons are easily stopped by solid objects, neutrinos play a key role in fundamental physics, helping scientists understand processes like fusion in stars, which differ from the nuclear structure roles of protons and neutrons. Neutrinos are nature's most elusive particles. They are created in nuclear reactions within stars, supernovae, and even our own sun. These subatomic phantoms have almost no mass and carry no electrical charge. A single neutrino could theoretically travel through a light year of solid lead without leaving a trace, a property that makes them both fascinating and notoriously difficult to study. But why are scientists interested in neutrinos? The quest to understand these particles is important for several reasons. Neutrinos carry crucial information about nuclear fusion processes within stars. They serve as early warning signals for stellar explosions. However, Their study provides insights into the mysterious dark matter that comprises much of our universe, and understanding neutrinos might explain why our universe contains more matter than antimatter. Different research facilities worldwide employ varied approaches to catch these ethereal particles. CERN's Large Hadron Collider creates neutrinos through high-energy particle collisions, but other observatories use massive underground detectors filled with specialized materials. Japan's mountain-based approach has a slight advantage over CERN's choice of location, but we will talk about that later. The detection process requires extraordinary precision and patience. Catching a neutrino is like trying to spot a specific grain of sand on all the beaches of the world while blindfolded. Scientists use massive tanks filled with ultra-pure water surrounded by light sensors. When the rare interaction between a neutrino and a water molecule occurs, it creates a flash of light, a tiny spark that reveals the neutrino's presence. This detection method, pioneered in Japan, has led to groundbreaking discoveries about neutrino oscillations and mass. With the basics of neutrinos covered, let's discover why scientists are tunneling below ground to capture them. Why build underground? The Hyper-Kamiokande project's location is a brilliant choice. A massive scientific instrument built deep within Japan's mountains, using nature as its protector. But why go through the trouble of hollowing out a mountain? The answer lies in the unique advantages that this mountainous setting offers for neutrino detection. Japan's mountains provide an excellent environment for studying neutrinos. The thick rock formations act as a natural filter, blocking out unwanted cosmic rays and radiation that could disrupt our measurements. By positioning the observatory 600 meters below the mountain's peak, they ensure that external disturbances have minimal impact on their experiments. The geology of the area also plays a crucial role in their success. The rock above them acts as a protective barrier, equivalent to 1,750 meters of water. The surrounding rock filters out 99.9% of cosmic radiation, and being underground means that there will be consistent temperature and humidity levels. These geological features create an ideal environment for their sensitive instruments. The density of the mountain's rocks is just right. It blocks cosmic rays while allowing neutrinos to pass through unhindered. Also, the unique geological characteristics of Japan make it particularly suitable for building underground observatories. Japan's mountains contain stable, hard rock formations that are perfect for large-scale excavation projects. This gives them the perfect balance between accessibility and isolation, close enough to civilization for practical operations, yet sufficiently removed from human-generated interference. Building underground helps them tackle multiple challenges at once. The natural insulation provided by the mountain means they don't need expensive artificial shielding systems. Plus, being underground protects their massive water tank and sensitive photodetectors from temperature changes and weather-related disturbances. Japan's mountain-based location for the Hyper-Kamiokande detector has the unique advantage of shielding it naturally from cosmic radiation, thanks to the thick rock layers above. This depth helps create a low background environment, which is essential for capturing elusive neutrinos that are difficult to detect amidst cosmic noise. Unlike CERN's Large Hadron Collider, which is built beneath a relatively shallow ground level on the French-Swiss border, Hyper-Kamiokande's mountainous setting allows for more precise neutrino detection without interference from surface-level radiation or other particles. This natural shield makes it ideal for studying faint neutrino interactions from distant cosmic events, such as supernovas, with greater clarity. The structure inside the mountain allows them to construct the world's largest underground water tank, something they couldn't do on the surface. This combination of natural shielding and structural support makes it possible for them to build an observatory capable of detecting even the faintest neutrino interactions. Thanks to Japanese engineering expertise, this natural advantage has been turned into an incredible feat of technology. During excavation, they carefully preserved the mountain's structure while creating enough space for a detector that stands 309 feet high and 227 feet wide. This achievement shows how they can adapt natural landscapes for advanced scientific research. Building in a mountain is no small feat, but it's part of a larger journey. Next, we uncover how a once silent mining town became a hotspot for groundbreaking physics research. The Kamioka legacy. Deep within Japan's Gifu prefecture lies a remarkable tale of transformation. The quiet town of Kamioka, once bustling with zinc miners, has evolved into a global epicenter for groundbreaking particle physics research. This dramatic shift began in the 80s when scientists recognized the unique potential of Kamioka's abandoned mining tunnels. The story of Kamioka's scientific journey started with the original Kamiokande detector in 1983. This pioneering facility made history in 1987 by detecting neutrinos from a supernova explosion in the Large Magellanic Cloud, a breakthrough that earned Masatoshi Koshiba the 2002 Nobel Prize in Physics. The success of this initial venture sparked a scientific revolution in the region. Building on this momentum, researchers developed the Hyper-Kamiokande detector in 1996. This massive underground facility features a 40-meter-tall tank filled with 50,000 tons of ultra-pure water, 11,146 highly sensitive photomultiplier tubes, and advanced detection systems capable of capturing rare neutrino interactions. The Hyper-Kamiokande's achievements have reshaped our understanding of the universe by proving that neutrinos can change between different types, challenging standard physics models. It has also helped resolve the mystery of missing solar neutrinos and conducted groundbreaking studies on particle stability. The facility's success has attracted scientists from across the globe, transforming Kamioka into an international research hub. The site now hosts multiple cutting-edge experiments, from the KAGRA gravitational wave detector and CANDLES double beta decay experiment to NEWAGE dark matter search. The Hyper-Kamiokande project represents the next evolutionary step in Kamioka's scientific legacy. With its unprecedented scale and sensitivity, this new detector promises to push the boundaries of neutrino physics even further. The project builds upon decades of expertise gained at Hyper-Kamiokande while incorporating revolutionary new technologies. This rich history of discovery and innovation has established Kamioka as the perfect location for the ambitious Hyper-Kamiokande project. The expertise developed through years of successful neutrino research provides a strong foundation for this next-generation detector, promising even more groundbreaking discoveries in the years to come. Neutrino timeline from discovery to Hyper-Kamiokande. Neutrinos have an intriguing origin story dating back to the early 1900s. The tale starts in 1930 when Austrian physicist Wolfgang Pauli suggested their presence to account for the absence of energy in beta decay reactions. Pauli proposed that an unseen particle was to blame for carrying off this energy, introducing the term neutrino, which translates to little neutral one in Italian. 2 decades passed before the initial experimental proof of neutrinos. In 1956, Clyde Cowan and Frederick Raynes devised a clever test utilizing a nuclear reactor to produce antineutrinos that is the opposite of neutrinos. They were able to achieve a major advancement in particle physics by capturing the faint signals produced when antineutrinos interacted with protons in water using detectors placed close by. As scientists continued their research, they aimed to explore the properties of neutrinos. In the 1970s, there were significant experiments such as the Gargamel detector at CERN, which showed proof of neutrino interactions and verified their involvement in weak nuclear reactions. This period set the foundation for important breakthroughs in comprehending neutrino oscillations, which is when neutrinos alter flavors, and this was further demonstrated by experiments such as Hyper-Kamiokande. Hyper-Kamiokande, situated in Japan, employed a large underground tank holding 50 million liters of ultra-pure water and played a key role in the discovery of atmospheric and solar neutrinos. The revolutionary discoveries made in the late 1990s showed that neutrinos possess mass, though negligible, questioning traditional beliefs in particle physics and resulting in a Nobel Prize for those involved. Building on this legacy, the Hyper-Kamiokande project emerged as an ambitious initiative aimed at probing deeper into the unknown of neutrinos. With its construction near the Hyper-Kamiokande site, Hyper-Kamiokande will feature a much larger detector, allowing for enhanced sensitivity to rare events and more precise measurements of neutrino properties. This project aims not only to refine our understanding of neutrino oscillations, but also to investigate potential connections between neutrinos and cosmic phenomena, such as dark matter and the matter-antimatter asymmetry observed in the universe. Behind every monumental project lies a series of complex construction phases. Let's take a closer look. Construction phases. The construction of Hyper-Kamiokande represents a masterclass in precision engineering, where every blast and excavation must be calculated to perfection. The journey begins with a 2-kilometer-long access tunnel, initiated in 2021. Using the sophisticated drill and blast technique, workers methodically remove rock in carefully controlled explosions. Each blast sequence follows a precise pattern, Initial pilot holes are drilled into predetermined points with explosive charges placed strategically within the holes, followed closely by a controlled detonation sequence to minimize vibration, and then removal of debris using specialized mining equipment. This phase also adheres to strict federal land specifications, ensuring safety and environmental compliance. 600 meters below the mountain peak, engineers face their greatest challenge, constructing a reinforced dome capable of supporting the immense weight above. The dome's design incorporates high-strength concrete reinforced with steel fibers, rock bolts extending deep into the surrounding rock with pressure sensors monitoring structural stability, and waterproofing systems preventing groundwater seepage. The current phase focuses on excavating the massive cavern that will house a water tank with a vital scientific purpose. This delicate operation requires layer-by-layer removal of rock, continuous geological assessment, real-time structural monitoring, and installation of temporary support systems. The excavation process must maintain a perfect balance between speed and safety. Engineers employ 3D modeling and continuous seismic monitoring to predict and prevent potential structural issues. Each cubic meter of rock removed brings unique challenges, from managing groundwater to ensuring ventilation for workers operating heavy machinery in confined spaces. The excavation team works in shifts around the clock, carefully orchestrating the removal of thousands of tons of rock. Special consideration goes into preserving the mountain's natural stability while creating this unprecedented underground space. Advanced scanning technology maps hidden fault lines and weak points, allowing engineers to adapt their approach in real time. As workers chip away at the mountain's core, they're not just creating a hole, they're crafting a precision instrument that will help unlock the universe's deepest secrets. With each explosive sequence and every cubic meter removed, this structure inches closer to reality. Next up is subscriber's pick. Look at this incredible image. Thousands of people clinging to a mountain, funneling through gaping entrances as if drawn by some unstoppable force. It's not just a hike. It's a peep into one of humanity's boldest scientific endeavors. Japan is hollowing out this mountain for something monumental: the giant water tank. A vessel the size of 100 pools lies hidden underground, waiting to capture particles that travel through the universe undisturbed. Deep within Japan's hollowed mountain lies a marvel of engineering that defies imagination, a colossal water tank designed to capture the whispers of the cosmos. This isn't just any water tank. It's a precision instrument that will hold an astounding 260 million liters of ultra-pure water, making it the world's largest scientific water vessel. To grasp the sheer magnitude of this tank, picture 104 Olympic-sized swimming pools combined. The tank stretches 4.5 times larger than the famous SeaWorld Abu Dhabi Aquarium, currently the world's largest aquarium. Yet unlike these recreational facilities, every drop of water in this tank serves a crucial scientific purpose. The tank's design harnesses a fascinating phenomenon known as Cherenkov radiation. When neutrinos, those ghostly particles that typically pass through matter undetected, interact with water molecules, they create a flash of blue light. This light, similar to the ethereal glow seen in nuclear reactors, occurs when particles travel faster than the speed of light through water. The walls of this massive tank will be lined with 40,000 highly sensitive photodetectors, as we said before, each poised to capture these fleeting flashes. These sophisticated devices can detect light signals 1,000 times fainter than what the human eye can perceive, transforming each rare neutrino interaction into valuable scientific data. The water itself must meet extraordinary standards of purity. Any impurities could interfere with the detection of these elusive particles. The facility will employ advanced filtration systems to maintain water clarity, surpassing that of pharmaceutical-grade purified water. This level of purity ensures that when neutrinos do interact with water molecules, the resulting light can travel unimpeded to the detectors. The tank's immense size isn't just for show, it's a calculated necessity. Neutrinos interact so rarely with matter that scientists need this massive volume of water to increase the chances of detecting these particles. Each additional liter of water adds to the probability of capturing these enigmatic cosmic messengers. The construction of this large tank presents unique challenges. The tank's walls must withstand enormous pressure while maintaining perfect structural integrity. Engineers have developed specialized techniques to prevent any leaks or contamination, ensuring the observatory can operate continuously for decades to come. The tank is just one piece of the puzzle now. We turn our focus to the sensors capturing each elusive cosmic interaction. Cutting-edge technology, the photodetectors. Equipped to process millions of signals, this advanced technology filters noise, isolating the rarest neutrino events. Detecting neutrinos is a huge challenge, like trying to see a firefly's light from the bottom of an Olympic-sized swimming pool. The Hyper-Kamiokande Observatory has come up with an amazing solution: 40,000 advanced photodetectors, each one a masterpiece of engineering. But how do these photodetectors work? These high-tech devices act as super-sensitive cameras, capturing light signals that are incredibly faint, about 1,000 times dimmer than what our eyes can see. When neutrinos interact with water molecules, they produce brief flashes of Cherenkov radiation, and that's exactly what the photodetectors are designed to spot. Creating these photodetectors wasn't easy. They had to be built to withstand extreme conditions like water pressure 6 times greater than normal atmospheric pressure. They are crafted for perfect performance at depths of up to 60 meters, with continuous operation for decades without any maintenance. Also, it has double the light detection capability compared to previous models. The new design represents a significant improvement over the technology used in Hyper-Kamiokande. By incorporating advanced materials and collection systems, the photodetectors can now detect single photons with unmatched precision. Setting up these delicate instruments presents its challenges. Teams of engineers must carefully position each detector with millimeter accuracy, ensuring that they are perfectly aligned for optimal coverage. This requires custom-built robotic systems and specialized tools to handle the fragile equipment in the confined space of the mountain cavity. The increased sensitivity of the new photodetectors opens up exciting possibilities for neutrino research. With their ability to detect fainter signals, scientists can now observe rare neutrino events that were previously undetectable. This could lead to groundbreaking discoveries about these elusive particles and their role in the universe. The combination of cutting-edge detectors and advanced data processing systems represents a significant advancement in particle physics research. Each photodetector is connected to sophisticated electronics capable of processing millions of signals every second. By filtering out background noise and identifying genuine neutrino events with impressive accuracy, this setup promises to revolutionize our understanding of these fundamental building blocks of matter. With the final pieces of technology in place, it's time to look back at the timeline that led to this cutting-edge facility. Timeline and milestones, a look back and ahead. The ambitious journey of Hyper-Kamiokande spans decades of meticulous planning, groundbreaking engineering, and unwavering dedication. From its initial conception in 1999, this revolutionary project has evolved through various phases, each marking significant progress in our quest to understand the universe's most enigmatic particles. The current phase focuses on the intricate process of cavern preparation. Teams of engineers work tirelessly to ensure perfect waterproofing of the massive chamber, a critical step before the installation of the sophisticated sensor network can begin. The next major milestone involves the careful positioning of the photodetectors, each requiring precise calibration and testing. The filling of the tank with 260 million liters of ultra-pure water represents one of the project's most delicate phases. This process must be executed with extraordinary precision to maintain water purity and prevent any potential damage to the sensitive equipment. Once operational in 2027, Hyper-Kamiokande promises to push the boundaries of particle physics research. Scientists anticipate groundbreaking discoveries about neutrino oscillations, potential insights into the matter-antimatter asymmetry of our universe, and perhaps even the detection of proton decay, a phenomenon that could revolutionize our understanding of particle physics. The facility's technological capabilities will continue evolving through software updates and detector optimization. Research teams are already developing next-generation analysis techniques to extract maximum information from each neutrino interaction. Machine learning algorithms will process vast amounts of data, potentially revealing patterns and phenomena previously hidden from view. The international collaboration of 21 countries brings diverse expertise and perspectives, fostering innovation in detection methods and analysis techniques. This global partnership ensures that Hyper-Kamiokande remains at the forefront of neutrino research, adapting to new technological advances as they emerge. As construction progresses steadily toward completion, the scientific community eagerly anticipates the wealth of data this sophisticated detector will provide. The facility's extended operational lifespan of several decades promises to yield discoveries that could reshape our understanding of the universe's fundamental building blocks. With milestones met and goals within reach, the scientific potential it brings is worth exploring. The potential impact, what neutrino research could unlock. From dark matter to the matter-antimatter imbalance, neutrinos may hold the answers we seek. The Hyper-Kamiokande project stands as a gateway to understanding some of the universe's most fundamental mysteries. The study of neutrinos holds the potential to crack open several unexplained phenomena in physics. These ghostly particles might explain why our universe contains more matter than antimatter, a crucial puzzle in understanding our existence. Enhanced neutrino detection capabilities could provide new insights into the nature of dark matter, which makes up approximately 85% of the universe's mass. Also, neutrino research challenges our current understanding of quantum mechanics, potentially leading to new theoretical frameworks. The technology developed for neutrino detection has sparked remarkable advances in medical science. The same principles used to detect neutrinos have led to improvements in PET scanners and radiation therapy equipment. Particle physics research has contributed to the development of proton therapy, a precise form of radiation treatment that minimizes damage to healthy tissue. However, detection technologies inspire new methods for medical imaging, enabling doctors to track disease progression with unprecedented accuracy. The ripple effects of neutrino research extend into practical applications. Neutrino detection principles help engineers develop better methods for identifying leaks and structural weaknesses in underground infrastructure. Also, advanced particle detection systems contribute to improved atmospheric monitoring and weather forecasting models. Research into particle interactions drives innovation in developing new materials with enhanced properties. The knowledge gained from studying these elusive particles creates unexpected technological breakthroughs. Scientists working on the Hyper-Kamiokande project aren't just expanding our understanding of the cosmos. They're laying the groundwork for practical innovations that could transform industries from healthcare to environmental protection. As detection technology becomes more sophisticated, researchers anticipate discovering new applications for neutrino physics in fields we haven't yet imagined. Beyond cosmic exploration, neutrino research offers practical applications with real-world benefits. Why should we care? Real-world implications of particle physics. As neutrino research advances, its effects ripple through fields like healthcare, energy, and even space exploration. The effects of particle physics research go beyond laboratories and have an impact on our everyday lives, often in ways we don't even realize. Whenever you use your smartphone's GPS for directions, you're benefiting from Einstein's theories of relativity, the same fundamental physics that underpins neutrino research. Medical imaging technologies like PET scans, which are based on discoveries in particle physics, have saved countless lives by enabling early disease detection. Advanced radiation therapy techniques for cancer treatment draw directly from particle physics research. Airport scanners use particle detection principles similar to those in neutrino observatories. Understanding particle interactions helps create more efficient solar panels and nuclear power systems, and improved radiation shielding for astronauts stems from particle physics insights. The Hyper-Kamiokande project sparks imaginations and drives innovation across industries. Young minds watching this mountain transform into a scientific marvel. See proof that the impossible becomes possible through human ingenuity and determination. A high school student gazing at blueprints today might design the next breakthrough detector tomorrow. Think of neutrino research as reading the universe's diary. These ghostly particles carry messages from cosmic events billions of light years away, from supernovas to black holes. By decoding these messages, we inch closer to answering humanity's most profound questions. Where did we come from? What is the universe made of? Why does matter exist at all? As we peer deeper into the fabric of reality through projects like Hyper-Kamiokande, we're not just expanding our understanding of physics, we're building a legacy of discovery that will benefit generations to come, proving that our greatest achievements often start with the simplest question, what if? The next time you hear about Japan's hollowed mountain, remember, you're witnessing history in the making, a chapter in humanity's endless quest to understand our place in the cosmos. This underground observatory might just hold the key to unlocking secrets that will reshape our understanding of existence itself. Thanks for watching. See you in the next one.